Hi, my name is Jonathan Thomas, and I am an educator here at the Louisiana Art and Science Museum. Today, we're going to be taking an in-depth look at the geologic content featured here in our solar system gallery. We will do that with the assistance of two experts in the field of geology. Let's meet them now.
Hi, I'm Michael Stone, and I study geology at Louisiana State University. This is a meteorite, or more simply put, a rock that falls from space and strikes the Earth's surface. Because meteorites come from space, they provide scientists a glimpse into the composition of rocky bodies in our solar system and beyond. This allows scientists to test hypotheses regarding how our solar system formed, and even gain insight into the formation of our own planet. Meteorites can come from other planets or from comets or asteroids. They can generally be classified into three main categories: iron meteorites, stony iron meteorites, and stony meteorites. Iron meteorites consist mostly of an iron-nickel alloy. They are the type of meteorite most commonly seen in museum collections, including here at LASM, where we have several examples on display. Despite this, iron meteorites are much less common than stony ones, making up just 5% of all observed meteorite falls. The reason they are so common in collections is their distinct appearance makes them easy to identify, and they can readily be found using metal detectors. Stony iron meteorites are the rarest type of meteorite, making up just 1% of all observed meteorite falls. These meteorites contain both iron-nickel alloy, like we find in iron meteorites, and silicate minerals, which we find in stony meteorites. Stony meteorites, like this one found in New Mexico, are the most common type of meteorite, making up a whopping 94% of all observed meteorite falls. Despite this, their earth rock-like appearance makes them difficult to identify for collection. Stony meteorites are made from silicate minerals, the same type of minerals that dominate the Earth's surface. A special kind of stony meteorite, called a chondrite, is made up of tiny particles that formed before and during the birth of our solar system, around 4.6 billion years ago. Here on Earth, there are three types of rocks: igneous, sedimentary, and metamorphic. The rock cycle shows us how the different rock types are related, but it's important to know that any type of rock can turn into any other type of rock. Igneous rocks begin as liquid molten rock, called magma, found deep beneath the Earth's surface. Magma cools slowly underground, forming rocks with large minerals, like we see in this granite. We call these intrusive igneous rocks. When magma reaches the surface through volcanoes or cracks in the Earth's crust, we call it lava. Lava cools quickly, forming extrusive igneous rocks. Because extrusive rocks form so quickly, the minerals in the rocks will be microscopic if they have time to develop at all. This obsidian is an example of an extrusive rock that formed too fast for any minerals to develop. Rocks exposed at the surface will be broken down by physical and chemical weathering. Physical weathering means the rock is broken apart by the forces of nature, producing sediment. Chemical weathering dissolves rocks and minerals into water. Weathered materials can be eroded away from their source and transported via wind, water, ice, or gravity to be deposited in a new location. Deposited sediment can compact and lithify, meaning turn into rock. Dissolved minerals are deposited by precipitating out of water. Sedimentary rocks include both rocks formed from sediment, like this sandstone, and rocks made out of precipitated minerals, like this limestone. Sometimes, when a rock gets buried deep underground, or when it's near things like fault zones or magma plumes, the rock can be placed under immense pressure and exposed to extremely high temperatures. This heat and pressure will change the original rock into a metamorphic rock. The pressure that forms metamorphic rocks can cause mineral grains in the rock to align, creating layers like we see in this gneiss. We call layered rocks foliated. Some metamorphic rocks, like this marble, are non-foliated. Non-foliated rocks have been changed by high heat, but were not necessarily exposed to the same pressures that form foliated rocks. Fossils, like this iridescent ammonite, are normally found in sedimentary rocks, having formed when a dead organism is buried in an environment with little to no oxygen, which limits decomposition. Ammonites are an extinct animal that once roamed and hunted in the ancient seas. They are classified as mollusks, an animal group that also includes snails, clams, and octopuses. Just like snails and clams, an ammonite shell was actually part of its body. Ammonites first came about nearly 400 million years ago, before the dinosaurs roamed the earth, and went extinct following the same meteor impact that wiped out the dinosaurs around 65 million years ago. This particular ammonite was alive during the Triassic period, around 200 million years ago. Notice how the colors on the ammonite appear to change when you look at it from different places. This change in color is known as iridescence and is caused by the changes in the way light is reflected by the microscopic texture of a mineral called aragonite when it's viewed from different angles. Aragonite coats the ammonite's surface and has actually been part of the shell since the animal was alive, meaning this is still the original shell. However, the shell probably looked way different in the past. When the ammonite was alive, the aragonite that it now coats its shell was bound up in a material called nacre, which is still found in modern seashells and is made of aragonite mixed with organic materials. The organic materials in the nacre were broken down over time, leaving behind only the aragonite. Iridescent ammonites, also called ammonites, are rare. In fact, the only place in the world they are found is in the Bear Paw Formation of Western Canada.
Similar to Jason, the Siphagnus is also from the same time period, around 66 million years ago during the late Cretaceous. However, Siphagnus is quite a unique marine animal. Siphagnus is the largest predatory osteichthyes bony fish that has ever lived. These large animals were fierce predators of the ocean at a length of anywhere between 15 to 20 feet long. The Siphagnus could open its jaws so wide that it could swallow other fish as big as 6 feet long whole. The Siphagnus had very long teeth used for latching on to its prey and a distinctive underbite which gave it the nickname bulldog fish. Siphagnus was a ferocious predator that would eat anything it could swallow whole, predominantly eating smaller fish such as Geological, but could have also eaten seabirds, pterosaurs, and even small mosasaurs. Siphagnus fossils have been found all over the world, with fossils found in North America, South America, Europe, and Australia. However, most of the best preserved specimens are from the Niobrara Chalk in Kansas. Siphagnus lived in the Western Interior Seaway, a large inland sea that split North America into two land masses and covered the Midwestern sections of North America. Two paleontologists, Joseph Leidy and Edward D. Cope, independently described and published new fossilized fish from late Cretaceous Kansas. Leidy named his specimen Siphagnus audax, and Cope named his specimen Portheus molossus. Once it was realized the two specimens were in fact the same animal in 1898, the rules of taxonomic dating stated that Siphagnus audax was the correct name. The name Portheus molossus became a junior synonym despite it being more well known, and the name is still, incorrectly, in use in some collections to this day. This is the Psittacosaurus, the parrot dinosaur, which is from the late Cretaceous period around 66 million years ago. It may come as a surprise to you that both Jason the Triceratops and the Psittacosaurus are both a part of the same family called Ceratopsians. Psittacosaurus was a primitive ceratopsian that possessed all of the evolutionary novelties of ceratopsians, including a rudimentary frill, a rostral bone with a narrow beak and flaring jugal horns, and only 3 functional toes on the front limbs. Similarly, both the Triceratops and the Psittacosaurus roamed in herds. The Psittacosaurus did not have horns like the Triceratops, but flaring jugal horns-like features on the side of its face, which may have been used for intimidation, mating displays, and for ways to identify each other. Jason would have been around 30 feet long and weighing about 2,000 to 3,000 pounds, while its little ceratopsian relative, the Psittacosaurus, would have been around 4 to 5 feet long and weighing anywhere between 66 to 220 pounds. Despite their size difference, you might notice a similarity: their beaks, which they use to graze on vegetation. Psittacosaurus is also the reason why many paleontologists theorize that Triceratops may have actually had quills on its body due to the two dinosaurs being directly related. The first Psittacosaurus specimen was found in 1923 in Mongolia by Henry Fairfield Osborn, but a Psittacosaurus specimen that was found in China had quills fossilized on the end of its tail, which was the leading factor for the theory that ceratopsians might have actually had quills. A paleontologist is a scientist who studies ancient life and the history of the planet we live on. Paleontologists often study the Earth through something called the fossil record. We study ancient life and our Triceratops fossil named Jason to try to understand what life was like on our planet millions of years ago. After all, our planet is 4.6 billion years old, which leaves a lot to be explored. An example of the results of our exploration is the Triceratops Jason, who was found by a rancher named Jason in Montana. Jason the Triceratops helps us better understand what life was like when he was still around 66 million years ago during the late Cretaceous period when dinosaurs still roamed the earth. The Triceratops was a large herbivore, or what many people like to call a plant eater. When Jason was alive, he would have been around the size of an African elephant, weighing about 8,000 to 12,000 pounds, which is about the weight of 2 to 3 cars. The most noticeable feature about Jason and many other Triceratops like him is the large shield and horns that adorn his head. These horns would grow over the entire life of the dinosaur. One horn was right above the beak and the other two were on its brow. Triceratops would travel in large herds similar to modern-day cattle. Traveling in herds, along with these horns, help protect them against predators like the Tyrannosaurus rex. Jason is an amazing dinosaur and helps further our understanding of what came before us, giving us insight into the history of life on planet Earth.
It's very exciting to learn new things about geology and life on Earth millions of years ago. We hope this experience inspires your curiosity and motivates you to keep digging into this fascinating topic. Thanks so much for exploring and discovering with us today.